Hello, everyone. Thank you for joining today's John Bacall Colloquium. I'm Jared Heiss, the Director of Science here at SURF. A few quick housekeeping notes before we begin. Today's talk will be about 45 minutes, followed by 10 to 15 minutes of Q&A. You can ask questions live by raising your hand in Zoom or by using the Q&A button. This talk is being recorded and will be available on our website, institute.surf/JBC, as well as on SURF's YouTube and Vimeo channels. To receive notifications about upcoming talks, visit the Connect link at the top of the institute.surf webpage. You can register for all scheduled talks at institute.surf/JBC. We now have a dedicated Slack channel to continue the conversation after each colloquium or to follow up later. A link to the Slack channel is in the Zoom chat. You're welcome to ask additional questions of the speaker or engage the broader group assembled there. The featured speaker will be available on Slack for up to 30 minutes following the talk. Now it's my pleasure to introduce today's speaker. Dr. K.C. Kong is a professor in the Department of Physics and Astronomy at the University of Kansas. His research spans physics beyond the standard model, including collider phenomenology, supersymmetry, extra dimensions, and Higgs physics, as well as astroparticle physics with a focus on direct and indirect dark matter searches. More recently, his work has expanded into artificial intelligence and machine learning, with an emphasis on quantum algorithms and quantum machine learning applied to fundamental physics. Before joining the University of Kansas, Professor Kong was a research associate in the theoretical physics departments at Fermilab and SLAC. He earned his PhD in physics from the University of Florida and his master's and bachelor's degrees in physics from Pusan National University in South Korea. His contributions to research and teaching have been recognized with numerous honors, including the University Scholarly Achievement Award, Department Graduate and Undergraduate Teacher of the Year Awards, the NSF EPSCoR First Award, and the Outstanding Young Researcher Award from the Association of Korean Physicists in America. I also want to recognize Casey for his strong participation in other institute programs such as SETUP and our Quantum Partnership Workshop. Now it's time to turn things over to Dr. K.C. Kong to learn about quantum frontiers in particle physics, from sensing rare decays to solving collider challenges. Dr. Kong.
Thank you, Jared, for the introduction. Hello, everyone. My name is K.C. Kong. I will be talking to you about quantum frontiers in particle physics today. Here is a brief outline of my talk today. And I assume that most of you may not be working in quantum information science. So I have some introductory slide, maybe half of my presentation today. And the second half, I will focus on a couple of specific examples of quantum device use within the particle physics. Before we begin, I should emphasize that I'm a theoretical particle physicist, and who is excited about machine learning and application of AI and quantum computing. I am not a quantum physicist, but I see a great opportunity using quantum technology applied in particle physics. Okay, so why are we talking about the quantum? Probably we hear a lot about the quantum revolution for past a few years. As you know, the US government started the quantum initiative almost about 5 to 10 years ago. But for past 10, maybe 20 years, things were quite different from what was happening about 100 years ago. We had quantum mechanics. Now, quantum mechanics is over 100-year-old physics. We still teach in our undergraduate curriculum. And then almost everybody these days actually have some kind of device in our pocket. And many of these devices actually are possible because of the quantum physics. But yet, a lot of people actually, we believe that the quantum physics still can be used for many other things. And this particular effort is actually given by active use of the entanglement. about before maybe 20 years ago, all of these quantum devices do not actively use the phenomena like entanglement, but more recently, we are aggressively actually studied using entanglement phenomena and applied to the quantum computing, quantum sensing, quantum simulations, and the quantum communications. So what is a quantum computer? So many people ask me, what is a quantum computer? So if you think about it, quantum computer, people think about quantum computers. What about our classical computers? So in the left bottom corner, we remember actually looking at these pictures about the gigantic computers, which was made many, many years ago. And this particular project, the ENIAC, was essentially, it was supported by US Army effort, surprisingly. Now, in the right bottom corner, almost everyone has a working computer in our pocket. Remember in the history, from the left side to the right side, computer always advances, but the price actually always went down, performance always increases. What about the quantum computers? Some people might think that quantum computers will replace our classical computer, but in my opinion, probably that is not the case. This quantum computer will need it still classical computers to obtain the best outcome. Quantum computers can do certain things faster than the regular computers because it uses a different set of the rules. So it's not really about the speed. It is actually about how many possibilities we can explore at once using quantum phenomena. In the left upper corner, this is a well-known IBM Eagle 127 qubit computer. And once you open the outside the lid, you see the beautiful chandelier-looking the quantum computer in the right bottom corner. So the exact price is not known, but the price of this 127 qubit Eagle computer is about tens of $millions, depending on what kind of service contract you get from IBM. In the past, this ENIAC computer, the budget was about $500,000 or so, which is equivalent to $7 million today. So considering this cost, the IBM quantum computer, this fancy-looking computer, is actually similar to our ENIAC computer in the history. So we have still a long way to go. So once you if you zoom in, an actual quantum device is in the middle of the screen. This little chip is the size of my hand. This is literally a quantum chip, and everything else is related to cryogenic system to keep the quantum device in the low temperature to suppress the thermal noise. We can actually use this quantum device for free. IBM offers a service, free cloud service, 10 minutes for everyone. And then for scientists like us, we can actually ask for the running time through DOE and NSF. And once you're done with this free 10-minute plan, unfortunately, we still have to pay. But again, we can apply for the NSF and then DOE for the computing time. So what is the quantum computing? So before we start talking about the quantum computing, let's quickly recap what is the digital computing. To me, digital computing is a manipulation of the bits, the study of the quantum, study of the classical n bit to the m bits. So manipulation of the bit computation is what I call the digital computing. To manipulate this kind of bit computations, of course, we need many classical gates, such as NAND, for example. So an XOR or 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 some other logical gate. Collection of those logical gates, I'm going to call them as algorithms. So in the quantum computing, bits are replaced with the qubits. And then this computation will be handled by a bunch of quantum bits. And the classical gates are replaced with the quantum gates. And the collection of those quantum gates, I'm going to call them quantum algorithms. So in the left side, we have examples of the classical gates. In the right side, we have examples of the quantum gates. These quantum gates are nothing but the collection of some combination of the Pauli matrices, and these are the unitary transformations. There are two types of the quantum gates. One is a unitary, the other is non-unitary. Non-unitary operations are related to the projections. It's not reversible. all other quantum gates are reversible and the unitary transformations. So these are the simple example of the quantum gates, and these gates are highly device and platform dependent. So what is a qubit? A qubit is nothing but the uninormalized two-dimensional complex vectors. And you can imagine that the qubit as a linear combination of ground state and the one state denoted by 0 and 1 inside the bracket. And then there is a very interesting way of representing qubit using something called the Bloch sphere. This is actually the unit length sphere. And then ground state, the 0 is denoted by the North Pole. And the one state, excited state, typically represented by the point on the South Pole. So then this general state psi can be written as a linear combination of two basis vectors. So in terms of metrics, it can be written in this form. And this coefficients and in front of 0 and 1 are written in terms of cosine and sine, trigonometric functions. These are what we call the amplitude. Once we make a measurement and this wave function, the quantum state psi is collapsed to either 0 or 1, and the probability of obtaining 0, 0 or 1 state is proportional to the square of the amplitude. And of course, the total probability is conserved, and then this coefficient square is sum up to be equal to 1. And entanglement is nothing but the entanglement tells us that these two qubit systems, for example, are intertwined, and the entangled meaning that they are actually non-separable state. So why are we talking about the quantum computing? Where this quantum computing is useful? So as we are hearing a lot about the quantum, and then this probably one of the best use of the quantum computing will be the cryptography. And surprisingly, this is very deeply related to mathematics problems, such as hidden subgroup problems, discrete logarithm problems. This is one of the method to encode the password in our cell phone. And then second example will be optimization problems and search algorithms. And of course, one of the best example of the quantum computing application within particle physics will be so-called Hamiltonian simulation, quantum simulation. We can literally simulate our physical system using Hamiltonian simulations. Another application is what we call the quantum machine learning. And there is no mathematical proof that quantum machine learning actually gives us a quantum advantage over classical computing. But nevertheless, many studies report that quantum machine learning method actually learns better with a small number of the data, therefore giving us faster conversions. And then we can use less number of parameters compared to the classical machine learning. But however, in my opinion, we still have a long way to go. In addition to all these studies that have been done in the literature in the past, we are still looking for the interesting problems that can utilize the quantum computers. So one quick example that I can tell you about inner product. So in the scientific calculation, we calculate inner product matrix manipulations all the time. Surprisingly, this is, in my opinion, is the simplest example where quantum computers are extremely useful. For example, let's assume we have a 1024-dimensional vector, A vector, denoted by A inside the bracket. Suppose we have a second vector, B vector, again, another 1024-dimensional vector. Now we want to compute inner product of between the two vectors. Then, of course, A dot B vector can be written as a sum of the product of all these components. So we need to have 1024 multiplications, 1023 additions. We have order of 1000 operations to be able to compute the inner product. Now, in the quantum computing, if you believe my word, then we only need 12 operations to compute the inner product between the two vectors. With the one ancilla qubit, one additional register qubit, and then 10 qubit to represent A vector, second 10 qubit to represent second vector B vector. So we need a total 11 qubit and then 12 operations, so we can calculate inner product between the two. So there is a significant speed up. This is what we call exponential speed up. So proof is actually very easy. I'm not going to go through the proof, but I just wanted to show you that proof is not difficult. Even undergraduate students actually can prove this can be done. Now, this is a very simple example of inner product between the two-dimensional vectors, A vector and the V vector. And then this in the middle of screen, this is how we will be computing inner product between A vector and V vector, leading to the 0.707 in this particular example. Now, in the quantum version, of course, we have to embed this A vector, 1 over square root of 2, comma 1 over square root of 2, in terms of qubit. And there is a way to do these things here. I'm not going to give you some of the details, but I'm just telling you that there is a way to embed this A vector onto a point on the Bloch sphere represented by this A vector, A state. B vector is 1, 0. So this is nothing but the ground state represented by North Pole. And inner product can be written by the Brockian notation in this way. And then now in the bottom of the screen in the middle, this is the algorithm that computes the inner product between the two. So if you go to the IBM and you can have this something called IBM quantum composer, you can actually literally drag and then drop, and then you can make the very simple quantum algorithm. You can click the button, then you can get a simulation result, as well as you can get a real hardware run. Now, why this is very useful in physics? In physics, of course, these two state vectors, psi and phi, generally, these are highly infinite-dimensional vectors. So for example, if we want to compute inner product between the psi and then a phi state, we'll be computing a psi star multiplied by the phi star multiplied by the psi, integrate over three-dimensional space. Once we discretize, we will have many calculations we need to perform. Now we can actually do this calculation using quantum computer. And then essentially this will give us exponential speed up over classical computations. Second example is what I call the math magic. This is actually one of the popular examples that actually the kids in the K-12 actually like. I always use this example in my quantum algorithm class. So the game actually works this way. So I'm going to show you the 6 different cards, and then I'm going to ask you to pick a one number between 1 and 63, and then I will show each card one at a time and ask you, oh, do you see your number on this first card, and do you see your number on the second card? I'm going to ask you the same question 6 times. Then I will get a yes or no for each card, depending on whether you see your number or not. Then using that information, I can figure out what your number was. Probably some of you already guessed what this game is. It's actually based on the binary. Since to save our time, I already picked a number for you for the discussion. And in fact, the numbers in the left upper corner always ends with 1 in base 2. And the numbers in the right bottom corner, for example, here, then these numbers always begin with the 1 in base 2. So if you tell me your number, yes or no, basically I can read off the your number in base 2. I can convert that number in base 10. I can figure out your what your number was. Suppose your number was 43. So then you see the 43 appears 4 different cards. Then our answer will be yes, yes, no, yes, no, and yes. In base 2, we go backward. So base 2, your number is 1, 0, 1, 0, and 1, 1. Of course, there is a commutative property. This base 2 number can be written as a sum of these 4 numbers in base 2. And each number here can be represented by the numbers in base 10. For example, 1, 0, 0, 0, 0, 0 is nothing but 32. 0, 0, 0, 0, 0, 1 is nothing but 1. Essentially, all these numbers are nothing but very first number in each card. So 32 is the first number in the last card, and then 1 is the first number in the first card. So whenever the other person says, I see my number on this card, I just need to add these numbers in the left upper corner. 1, 2, 8, and 32. So adding these 4 numbers are not too difficult. So then at the end, I can tell you that, oh, this number must be 43. So this is actually a very interesting game that you can play with a small child. And then now, of course, the most important question is there a way to find the answer by asking less than 6 questions? So if you play this game with the kids, and probably many kids will say, what is your number? That's what my kids actually asked me. But that's not the right question though, right? So here, what we are doing is that we have a problem. To solve the problems, of course, we have to figure out some kind of particular algorithm, particular method to solve the particular problems. To run these algorithms, for example, in this case, quantum algorithms, of course, we should be able to run the algorithm on a certain quantum device. To make that device, of course, we need to make materials. So I want to tell you that quantum information science requires 4 different pillars. One is the domain-specific research problems, and then the corresponding algorithms to solve the problems. We need a quantum device to run the algorithm. Of course, to make the device, we need to have a good solid background in terms of quantum materials. We need all 4 of these to find the great application of quantum computing. Coming back to the previous question, this algorithm known as the Bernstein-Vazirani algorithm, I believe this was developed in the 1990s by a computer scientist at Berkeley. And then I'm not going to go through the details, but basically that question that I ask you, do you see your number? That's not the right question. We should be asking the right question to be able to use quantum algorithms on a certain quantum device. You change the particular question in terms of some mathematical functions represented by f, and you can imagine some kind of a quantum gates corresponding to that function. So here the number of function called is essentially 1. Namely, that's why I claim that by asking one question, by calling this one quantum gate, by calling this one mathematical function f, I can get the answer. I can find out the answer. So this one actually uses the so-called the superposition of the quantum state. Now, another great application is namely inverting matrices. As you know, this inversion of the gigantic matrix is one of the bottlenecks in the quantum classical computation. And if you have n by n matrices, to find the inverse matrix, roughly you need to have n cubed number of operations. Now, if you have a lot of zeros, so-called sparse matrices, if you want to invert, you need roughly order of n operations. Now, in this particular paper about 15 years ago, and these authors actually claim that a number of operations needed to invert the sparse matrix is log of n. So therefore, quantum algorithm brings exponential speed up compared to the classical method. And this one kind of boosted something called the quantum machine learning and quantum algorithms for past few years. And then essentially the idea behind this is how we do the Fourier transformation more efficiently. And then the y-axis in this graph shows the number of operations, the amount of complexity. X-axis is the size of the array vector. So then the number of operations needed, the scaling actually goes like n squared for the regular discrete Fourier transformation. But FFT, fast Fourier transformation, the complexity goes like n log n. But quantum Fourier transformation, quantum version of FFT goes like a square of the log n. This is where the speedup comes in. Now, of course, this has been proven experimentally, and we cannot solve the very gigantic million by million matrices, try to find inverse matrices. However, some of these studies written in the bottom, they actually try to invert 4 by 4, 8 by matrices using a real hardware. Now, another reason why a lot of people, including myself, are talking about the quantum simulation, quantum computing is because there is a Python code freely available for everyone's use. And IBM offers what's known as a Qiskit. This is Python-based. And Xanadu, Toronto-based company, offers another very popular code known as Penny And Google also offers a TensorFlow Quantum that can be easily used along with the TensorFlow. And then NVIDIA offers something called the CUDA-Q. And in addition to all these quantum simulation code based on the Python, there are different ways of using quantum simulations. Because these tools are available, we can easily simulate on the classical computer, and we can actually submit exactly the same code to the real quantum hardware without any difficulty. Now, in the particle physics, in the high energy physics, of course, we have many tasks we want to perform. In the theoretical physics and experimental side, we have a certain task we want to accomplish. For example, we can try to understand the real-time phenomena in the lattice gauge field theory. And then in the experimental side, for example, classification problems and then regression problems. All these problems are strongly tied with the AI and machine learning method. And interesting in many of these machine learning method optimization problems are also strongly tied with the various quantum algorithms. So this particular slide is actually obtained from this summary report for quantum computing for HEP for a few years ago. Now, this is already 3 years ago. Now, more recently, there are a lot of activities involving machine learning and quantum computing. This particular working group initiated by the Coastal Action in Europe, and anyone is welcome to join. And if any of you are interested in application of machine learning and quantum computing for future colliders, I highly encourage you to go to their webpage and try to join the working group. Where quantum computers are useful? Probably there are some unknown areas the quantum computers are potentially useful, but these are the quick summary of the quantum computers may be potentially useful. Some of the places I worked on some of the areas, quantum optimization and the use of the quantum sensors, quantum simulations, and focus a lot on the quantum machine learning side, and also study the entanglement and then measurements of the violation of Bayesian inequality with the LHC data, focusing on the TT-bar production. But today, I will try to introduce a couple of examples how we use the quantum computers in the optimization problems in the dark matter searches. Quantum optimization. So the problem that I want to solve is what's known as combinatorial problems at the colliders. Suppose we do the PP proton-proton collision, and we produce lots of particles denoted by V1, V2, and Vn. And in our model assumptions, some of these particles may decay from particle A, denoted by blue. Some other particles may come from mother particle B, denoted by B. It doesn't have to be 222. It can be 221, 223. But let me assume that we are interested in 222 at the moment. And then let me further make an assumption that all the particles here, red and blue, are visible. However, let me make an assumption they are visible, but they are all jets. So then the question is, which of these particles came from particle A? Which of these particles came from B? This is what's known as combinatorial problem. So what is the best way, efficient way of assigning all observed particles into two decay chains? This is harder problems. And then I'm telling you that quantum algorithm may offer actually very tantalizing method that performs better than classical method. Now, before getting there, I want to tell you that there is another problem, what's known as maxical problems. Here, goal is to maximize the number of cuts edges in a graph. For example, here, the graph is denoted by 5 circles, 5 nodes, and then there are some connections. So the goal is to maximize the number of cuts in a graph when we try to split into 2 parts. So for example, in the graph in the left bottom corner, I can cut through the 2 dashed lines, then 1 and 2 belong to the one set. Remaining circles, 3, 4, 5, may belong to the second set. Then the number of cuts will be 2, because I need to cut a connection between 1 and 3. I need to cut connection between 2 and 4. In the right side, the right bottom corner, number of cuts I need to make is 5, 1, 2, 3, 4, 5. Then I can group this 5 node into 2 parts. I can partition this 5 node into 2. 1, 4 belong to the first set. 2, 3, 5 belong to the second set. This is what's known as the maximal problem. Another problem is so-called map coloring. So I'm going to this finite number of colors, and this is and then ask you to the color, each rectangles, each regions, and then that you can so that you can discriminate the boundary between the different the countries, the different boundaries. This is the kind of something that we used to do it when we were little. Map coloring problem, and then another problem, very well-known problem, is what's known as traveling salesman's problem. So you start with one of the node, and you visit all different sites, and come back to the very first one. And what is the most efficient way of visiting all sites? So this edge, along with the number, you can say that all these numbers represent how long it takes. It can be interpreted as a distance between the two. It can be interpreted as some kind of resources you need to use to move from A to B, B to C, and so on. So what is the best way to maximize your action value for these things to visit all different sites? All these problems, what's known as NP-hard problems, and this is actually one of the important problems in the theoretical computer science, which will actually tell us about NP equal to N each problem. The reason why I mentioned all these problems is they're exactly the same problems mathematically. And then these problems actually known as quadratic unconstrained binary optimization problem known as QUBO. So the name of the game here is that assume that there is some function f which maps n-bit string into a real number. For example, it can be a complex number, but let's say a real number. Then this function is written as follows in the middle here. Xi times xj multiplied by some quadratic coefficient qij, and there might be a linear term here. X takes either 0 or 1, so this is a 1 bit, and all these coefficients q and h can be in general real number or complex number. Then here the goal is to minimize this function and then find, here goal is to find the binary vector x that minimizes function f. So this is the f of x is what's known as the cost function. You can call it Lagrangian, you can call it Hamiltonian. The f of x is the minimizing f of x is our goal here. Now, all these problems that I mentioned earlier in physics, this is what we call the Ising model, fully connected Ising models. And all these problems in this on the screen, including the examples that I showed a few slides ago, all these problems can be rewritten in terms of a quadratic problem. And then sometimes we call this thing as a Markovich model. If you work in the finance, we call it Sherrington-Kirkpatrick model. If you work on the condensed matter physics, if you're excited about the machine learning, this is what we call the Hopfield model. I mean, it's not exactly the same, but at least all these quadratic problems looks very similar to each other. And then exactly the same problem have been applied to the many different areas of the optimization problems in terms of drug discovery, material discovery, even trying to find the best route in the traffic. And then, so the example that I want to solve earlier, I mentioned was the combinatorial problems at the colliders. Now, by a simple embedding of something called a binary encoding, binary embedding, I can introduce a binary variable x for each particle. So if particle I belongs to the model particle A, if ith particle decays from A, I can assign 1. If that ith particle belongs to the model particle B, I can assign 0. Then form momentum of A particle, PA, P1, can be written as a linear combination of little pi. Little pi is nothing but momentum of the individual visible particles multiplied by this binary bit value xi. And then momentum of the B particle, P2, can be written pi times 1 minus x. So this way, the P1 is represent the momentum of A, P2 represent momentum of B particles. Now I need to find my objective function. So I'm gonna make an educated guess, namely that this particular problem happens at the Hadron Collider. At Hadron Collider, as soon as you get to the threshold, then the number of events, the cross-section increases very rapidly near the threshold and then dies out very rapidly. So what I'm gonna do is I'm gonna introduce some kind of objective function that I call H as a mass difference between the two particles. To observe the sign, I'm gonna do the square of the mass square difference. And interesting, this gives the right dimension. This is dimension 4 operator now. Now, this is my objective function. I can call it the loss function. I can call it the cost function, or I can call it Hamiltonian. Now, with this, if I plug the my definition of momentum of A and B into the Hamiltonian cost function, then you do the full expansion, then my Hamiltonian just becomes the Ising model. Once I introduce spin variable s, changing from x to s, that I can get the quadratic Hamiltonian. So I have assumed that two particles may have the same mass, but they don't have to have the same mass. This H0 Hamiltonian is given in terms of in terms of mass square difference. To consider the asymmetric production of A and B particles, I'm going to add second term, which is the sum of the two masses, and I'm going to call it H1. I'm going to add this H0 and H1 with some kind of hyperparameter lambda. This H0 plus lambda H1 will be my full Hamiltonian. Lambda is some kind of hyperparameter I have to tune. So I'm going to make an educated guess what lambda value should be. Interestingly, this HP Hamiltonian or loss function or cost function everything is a quadratic form. And there are many different algorithms which allow us to simulate this particular quadratic Hamiltonian. One of the well-known algorithms is what's known as quantum approximation optimization algorithm, QAOA. This has been applied to the many different tasks, as I mentioned in the previous slide. And then the way it works is that you start with some kind of randomly initialize the state, and then once you continue with the time evolution with your problem Hamiltonian, and certain states actually obtain the higher amplitude, or other irrelevant states actually gets suppressed by construction. And at the end of the day, you have 2 to 3 different states, which actually very high amplitude. And then you hope that one of them actually gives the solution to your problem. Because this particular state has the highest amplitude. So when you make a certain number of measurements, whichever give you the highest frequency, they will give you most likely solution to your problem. So what we have done with my collaborator was that we have actually utilized many existing algorithms and then compared against what's known as the hemisphere method and the classical machine learning. So here is the result. Sorry, this is a little bit complicated, but the y-axis is what's known as efficiency. How well we resolve the combinatorial problem for a particular example that I have investigated, namely the full hadronic production of TT bar. In this problem, there are 6 particles, 6 quarks in the final state. So I'm gonna try to assign 3, which of the 3Z came from the top, which of the 3Z came from the anti-top. I'm not going to assume that 3 and the 3, it can be 2 and 4. I'm gonna be agnostic about how many particles come from top or anti-top. But I'm going to assume there are 6 particles. 6 particles must be assigned one or the other. In this case, the best way to represent performance of the method is in terms of something called how fast top quarks are moving. So x-axis is what's known as the x-axis is the TT bar invariant mass divided by the top quark mass. So x-axis basically tells us how fast the top quark was actually moving. So here is a map between the value of invariant mass to the speed of the top quark. So this x-axis is equal to 1, which is the left side of the graph. That means the 2 top quarks are produced at rest. If mt over 2 m top is equal to 3, corresponding top quark speed is about 94% of the speed of light. So when we move from the left side and to the right side along the x-axis, top quarks are moving faster and faster and faster. Because top quarks are moving fast, it is relatively easy to resolve the combinatorial problems. Therefore, all this classical method, what's known as hemisphere method, which is shown as a dot dashed line, actually performs better when you move along the x-axis. Now, all other lines, solid lines represent the result obtained using quantum algorithms. And the left side plot shows the result using the first part of the Hamiltonian. And then the result in the right side uses something called the full Hamiltonian, as I showed you earlier. So this actually gives us the quantum algorithm, as you see, the reach is much higher than classical method, known as hemisphere method. So in this quantum algorithms, we do not use a top quark mass. We do not use a mass of the intermediate particle W mass. We do not assume anything about the particle masses. Now, this is a quick summary table. These two rows, hemisphere taboo method is a classical method. Taboo is another search algorithm used by computer scientists. This actually performs quite well, actually better than hemisphere method. And in the middle section, I'm showing you the result using quantum algorithms. In the last row is the result using the attention-based network using classical machine learning. One of the issues with the classical machine learning is they require a lot of training samples so that we can use a lot of parameters, and performance is great. And on the other hand, the quantum algorithms do not need the training parameters. We can find which particle came from the which model particle for event by event for each event. And then this one uses a very little number of parameters. So that is the main difference between the classical method and the quantum algorithms. So currently, I'm trying to generalize this to a case with the beyond 6 qubit, because in the particle production, typically we observe several hundred, maybe 1,000 particles in the final state. So our actual hadron collider collision is much more complicated. And not just the 6, we have several hundred particles. Can we solve this kind of combinatorial problem? So this is something that I'm currently working on. And there are a lot of examples. What about the ISR? How do you take care of the ISR issue? What about the example with the missing particles in the final state? There are some possible the method to take care of these things, but so far no one has addressed these issues. And what about the high order terms in this Ising model, which has a quadratic term? Can you actually extend including high order terms? Does that help? What about can you run this into real hardware? And then what about the error correction? So all these questions are great, and this is something that needs to be done. So for the remaining of few minutes, I want to quickly mention about how we use the quantum sensors for the rare decay of the dark matters, potentially cosmic neutrinos. So I'm going to quickly mention something called the transform qubit. Transform qubit is nothing but the LC circuit where the coil is replaced with something called Josephson junction. Therefore, the harmonic oscillator spectrum is actually breaks the non-harmonic oscillator. The equidistance potential energy is replaced with this nonlinear term, with a cosine-looking potential term, where the energy spectrum is actually not equal to each other. So as long as we operate this particular device with the lowest, the frequency corresponding to the two lowest state, then this effectively, state, Josephson junction state, becomes the system of the level 2. Now, experimentalists actually make things a little bit better, introduce this second Josephson junction, so that we can actually control the frequency corresponding to the two lowest level. This is what's known as a squid device. And then particularly transform qubit operating frequency is about 1 to 10 gigahertz. This is a microwave range, about tens of centimeter wavelength. Now, all these quantum devices are generally surrounded by some kind of a cavity to shield the contamination coming from the outside. And then also inside there is a cooling device, so we can actually suppress the thermal noise. But as you know, there are two types of particles which can penetrate through this kind of shielding. One is a dark matter, the other is a neutrino. So if dark matter and neutrino somehow induce photon that fall within this frequency band, 1 to 10 gigahertz, then in principle, those photons can resonantly excite the qubit. Therefore, we can turn this kind of dark matter interaction into the errors in the quantum computers. 1 to 10 gigahertz roughly corresponds to tens of microelectron volts. And so the basic idea is that you initialized all the qubit to the grounded state represented by 0. And then at some point, dark matter comes in, generates some kind of electromagnetic photon, which will mess up your qubit. So then this naturally time evolution will lead to grounded state and the one state with some amplitude comes from dark matter physics. Then when you make a measurement, naively, since we started from the grounded state, we have a high probability of measuring the grounded state. There is a non-negligible probability obtaining the one state. This one actually comes from dark matter physics. So by measuring the probability of getting the one state, we can say something about the dark matter physics. So this idea has been proposed by a colleague in the University of Tokyo. So they have applied this idea to hidden photon dark matter of the dark matter mass of the microelectron volts range. And this has been generalized to some other scenarios. For example, myself and a colleague, we talked about decay photons and illustrated that there is a certain parameter space that actually the transform qubit quantum computers can actually probe. And then unfortunately, I'm running out of time, but I want to mention that this is actually very different from conventional quantum device, because if you have a two quantum device, generally sensitivity of the signal grows like n if you have an n quantum device. However, main difference between the qubit-based device and regular quantum sensor is actually the entanglement. Because qubits are entangled, that you can expect that due to the entanglement, actually the signal sensitivity, it can be much higher than a regular device, because you can run the quantum algorithm with the qubit-based sensors. And then I will finish up by showing that this particular range, 1 to 10 gigahertz, happen to coincide with the mass range, frequency ranges of cosmic neutrinos. So there is a very tantalizing coincidence that the transhuman qubit frequency range happen to be related to cosmic neutrinos. Therefore, it is possible to use qubit-based sensors to look for cosmic neutrinos. So I will leave this and then show you the final slide, and then I will take the questions. Thank you for your attention.
Dr. Kong, thank you much. That was a fabulous talk. Thanks for bringing us from our everyday into the quantum space and your enlightening descriptions of thinking about problems through a quantum lens. And I particularly appreciate the characterization of errors as data as we look for new phenomena with dark matter, for instance, and possibly very low energy neutrinos. Let's see if there are questions here. I'm going to go into the chat. Here's the thank you. Just as a reminder, if you have a question for our speaker, I can raise your hand or put that question in the chat or in the Q&A. Question here, what is the future of quantum computing at SURF or underground in general, if you have any thoughts on that?
Well, I guess this question is for you, Jared.
Yeah. We are very interested in hosting a quantum facility underground, getting back to the errors as data, being able to shield some of these qubit systems or other quantum systems from cosmic ray muons. Then you can reduce or increase the sensitivity for some of these new physics phenomenon. So that is part of our strategic plan going forward. We're very excited. One of the reasons that some of our programming is really dedicated to exploring quantum mechanics and quantum discussions, not only on sensors and quantum computing, the quantum communication that you mentioned earlier, Casey, those are all very exciting for us. Another question here, discuss directional dark matter idea.
Yeah, I apologize. I skipped the some of the important discussion over here. Um, just so what happened over here is that some of you may know that USA is putting a lot of efforts toward something called the quantum communication and quantum network. For example, I'm in this particular slide, I'm showing you the proposed idea of the quantum network by the Stony Brook and the Yale and Columbia, a few places in the northeast area of the US. And basically the idea is that two qubits are entangled via some kind of classical photons through the fiber optics. So for example, over here in the Columbia and the Yale, they are Stony Brook, for example, they have two entangled qubit, which are tens of kilometers apart. But then extremely ultralight dark matter comes in, and they might actually hit one of the qubits. And since two qubits are entangled, and then you use actually the fact that two qubits are entangled, and you from that information you can have some estimation from which direction dark matter actually might have flew into the qubit sensor. So there are some studies done by again the colleague at the University of Tokyo. Once again, the idea here is if you look at the slide, assuming two qubit sensors and the 1 and 2, these are very far apart, tens of a kilometer or so, or can be even larger. Then main difference between the two here is that because they are apart by the distance delta r, and the phase difference between the two qubits will be given by this factor over here in the where that I'm pointing, k times delta r. K is the dark matter, the momentum of the dark matter flow, and delta r is something that we know already. And then this phase difference is the something that give you information about dark matter flow. And then we can cook up some kind of a particular measurement protocol. And this M protocol is that utilizes entanglement between the two qubits, which are apart from each other. And then what this group has shown is that the number of measurements that you can make as a function of the particular x-axis involving the speed and then angle. Angle is the angle between the delta r vector, which points to two qubits. So this is the angle between the two delta r and then a qubit with respect to the galactic center. So this data is some quantity that tell you something about the directions. So not only the magnitude, some information about the directions. And then I did a very quick study, for example, two velocity distributions. SHM represent standard halo models. And then here, dashed line is, for example, analytic description of the Gaia fortified distributions. We can actually see the difference between the two when you try to make a measurements. So two plots in the left are results using the standard halo models. Two plots in the right from the different distributions based on the Gaia observations. So by measuring the number of by making a number of measurements as a function of the angle or speed, you see the different behavior. So indirectly, we can get information about what kind of velocity distribution of dark matter we are looking at. Once again, there are only very few handful of papers came out right now. We need more ideas to apply this kind of dark matter physics utilizing quantum network channels. I hope this gives you a little more information about the directional detection.
Great. Another question here in the chat. You, in your presentation, talked about collider data sets. And the question here is, can you search in those collider data sets for evidence of quantum entanglement, Bell's inequality, or concurrence of those, and whether that can shed light on new physics?
Yeah, so that particular example that I showed you in my presentation was a quantum optimization problem. So I was literally trying to solve, again, which particle came from which model particle A and B. So this is a little different from a study on the entanglements and the violation of Bell's inequality. So as many of us are aware, LHC and the Atlas and CMS collaboration declared that actual entanglement of TT bar, for example, in the dilepton semi-leptonic channel, entanglement has been observed with a great significance. However, the violation of badge inequality has not been observed yet, and entanglement observation was done near the threshold. There are two regions of Faraday space where two top quarks are extremely boosted and where two top quarks are actually entangled. And also near the threshold, the two top quarks can be entangled. So currently, if I remember correctly, the entanglement of the top quark has been observed near the threshold, but I know there are some studies. I think experimental will be continuing observing entanglement in the boosted region as well. However, violation of badge inequality is much harder because you have to look at the smaller set of the data to avoid the contamination. And as far as I understand, the observation of the violation of badge inequality near the threshold in the dilepton channel is impossible. So you will have to go to the extremely boosted region. Because we have to utilize the boosted region of the top quark, TT bar production, probably it makes sense to consider the semi-leptonic channel instead of the dilepton channel. So that is actually what I have proposed. As far as I understand, both collaboration actually working on that. And then according to our naive study, and we think we can observe violation of badge inequality in the boosted region with the top samples about at the level of 4 sigma level. I'm not sure, but I know experimental colleagues, they always do better at the end of the day. I'm hoping that we can have some evidence for the violation of the badge or proof of the quantum mechanics at the end of the day. I'm not sure whether I'm answering your question, but okay, so yeah, so quick, yeah.
Another question in the Q&A section, and actually I had the same question, so I'm glad this was asked. You described quantum optimization of the collider data sets, and the question here is there any effect on previous results? Are these new algorithms finding different results? And are maybe another way of asking that question, are quantum algorithms being applied to previous data sets? Are people mining data that's in the can and has been for many years?
No, answer is no, not yet. So that's the goal, right? But of course, there are challenges. And the problem is that because of, for example, in this particular example, hadronic production of top quarks, we do not reconstruct the top quarks in the hadronic channel because of LHC environment is complicated. I made a very simple assumption as a theorist. Does this method work in this idealized situation? I claim that in the idealized situation, algorithm works. However, in reality, it is, as we know, it is much more complicated. So the actual application of this kind of optimization problem has not been applied to the actual data yet. However, there are different applications. For example, classification problems. Some particular studies using quantum machine learning idea, sometimes it performs a little better than classical machine learning algorithms. Unfortunately, downside is many of those problems to apply with actual data, it requires a lot of qubits. So unfortunately, the ideal level, I believe it is working fine. We know where we might have a quantum advantage, but in reality, unfortunately, many of those specific examples require the many qubits. So we are not there yet. So I would say that is a great point. And then I'm gonna mention one more time. Our quantum computers are, we are actually at this era, 1950s, in terms of quantum computing. Great promise, but we still have a long way to go.
Very exciting. Well, why don't we wrap things up for this installment of the John McCall Colloquium. A reminder that today's talk will be available to view and share on our website, institute.surf/JBC, as well as YouTube and Vimeo. Next month's John McCall Colloquium will be a hybrid event hosted on July 8th at our standard time, 9 a.m. Mountain. And the topic From a few solar neutrinos to the quantum entanglement of many trillions of neutrinos, with featured speaker Dr. Baha Balantikan. As a reminder, please join us on Slack right after this talk to continue the conversation with Dr. Kong and others. The link is in the chat. Finally, we value your feedback. Please take a moment to complete the short survey you'll receive in Zoom and by email. Your suggestions on future speakers and topics help ensure this series remains relevant and useful to the community.